back to my next video. I received many comments through shared sites such as Reddit, Instagram, here on YouTube about using the text-to-speech method of presenting my topics. So it was agreed that not many of my viewers like the method, so here I am presenting the next chapter in my series on CNC. Okay, in this episode we will discuss your base table in a bit more detail and ensure that your pride and joy will not move in a way that will ruin your job or worse, damage your machine. Secondly, we will talk about material choices for your actual rig and the pros and cons for them. In the last episode we touched on several topics, and most important topic that I'm going to repeat is that the weakest part of your machine is the part that is given the least consideration, or the weakest part of your entire build. Okay, you have your workspace and hopefully a secure floor to mount your work table. Your work table can be made from timber or steel. Some builders use aluminium extrusion for their table, but in experience you're looking for stability and weight to do this right. So you can generally frame up your timbers as you like. There are many design ideas available online, but the rule of thumb is the stronger you make it the better, but you can over-engineer this section and consume valuable budget. A useful part of building a strong table to understand is bracing. You can use a smart amount of timber by utilising correctly applied bracing. Many building plans will advise the general principle of 2/3. Okay, so taking this into account, let's give you an example. But knowing the size of your machine and the area it will take up, you can build your table. Now, you need to measure up from the floor to 2/3 of the table leg, as in the diagram shown. Your brace will reach here. Now, the other end will come down to the floor and be mitered or bolted to lock into your opposite leg. Once you have worked the first out, it is easy to do the others and complete and lock your table in. If done correctly, you can push around on each side and it won't move very far, if at all. Add more bracing if you feel the need. So that's it for a wood table. If your rig is not planning on cutting at light speed, then this will do well. But if you're intending on running your rig on a potentially business level, you may require something more durable. In this case, steel. If you follow the above method, you can build a table that is even stronger. If you are a competent welder or know a mate who can weld for you, then a welded frame is the best you can get. But bolting can serve just as good as long as you ensure 2 bolts at every join and the gauge of your steel is better than 3mm. Fantastic, we've got a strong and stable work table. Onto the fun bits, designing your actual rig. So before we keep going, this channel is about people who want to be able to build a DIY CNC machine from scratch. Okay, so what are the basic components of a mechanical build of a CNC rig? The electrical side we'll approach later. So 1, X-axis and linear motion gear, 2, Y-axis and linear motion gear, and 3, the Z-axis and linear motion gear. Before we get into this section, I can advise that CNC rig design is an interesting subject. You have to be prepared to reverse engineer a lot of things. In saying this, don't let this put you off, as it can teach you a heck of a lot without even buying anything. I made the mistake of buying a pre-designed kit from online only for it to be not what I wanted. The cost of upgrading the DIY kit has ultimately cost me a lot more than it would have if I had researched more and designed my own rig. Okay, on to what you want to make your baby out of. I'm not going to lie, the rating in order of best to least effective materials is this. You have steel, then aluminium plate and a combination of extrusion, thick acrylic, plastics or laminates, and then the lowest is wood. But a combination of greater and lesser can also add up to making a truly formidable machine. I advised before, when it comes to a DIY CNC design, you have to reverse engineer your build. So firstly, you need to decide what you want to do with your machine. Do you want to work with aluminium, wood, plastics, paper? Do you want to cut, mill or draw? The decision you make here will determine everything you decide in the future, but generally aim for the hardest thing to work with, and in this case it's aluminium. If you're asking why not steel, well, you can cut it, but putting it this way basically, metal milling machines are incredibly strong, and when you design one of these machines, you most likely won't cut anything more than what the rig is built from. And if you try, then your effort and time taken to do so will most likely have errors and will ruin your piece of work. So let's get back to it. You've decided what you want to make your rig from. Let's use steel in this exercise. One of the parts you will need to reverse engineer is the gantry plates. Grab yourself a pen and paper and write down a few notes here. I will guide you through the process step by step, as it will make it easier. So on your paper, draw a rectangle, one that has a height greater than width. This drawing won't be to scale, but it will allow you to make sure you can calculate your overall size. Let's begin with the height of your plates. Several factors come into play here. You need to add a wasteboard or sacrificial board that will fit to your table. Generally, anything up to 32 mm, but not less than 12 mm is best. What is a wasteboard or sacrificial board, you ask? It is a piece of material used on many routers that can be honed flat every few runs or so to keep things accurate, and if you're using a vacuum table, then a strong suction hold. More on vacuum tables later. If you're wanting to work with aluminium, I would suggest an aluminium baseboard. This will allow you to drill fixturing points into it for work holding whilst working with aluminium if you need. So, let's moving on. We'll use 32 mm MDF. If you are milling aluminium and wood, etc. on the same machine, you need to have a good idea of the result of the next section. But to be polite, you need to choose a maximum thickness of your desired working material. Many machine designers choose to run a potential fourth axis, also known as a rotary axis. This will then be used to make objects like table legs and baseball bats. But I digress. Let's just work with flat stock with a maximum depth of 100 mm. Fence posts. Yes, I know why you ask. No reason, it's just the thickest you'll most likely find as the stock material. And the room will allow you to set up a rotary axis. So, on your rectangle, working your way up from the bottom, make a mark that is 132 mm from the bottom. This accounts for your wasteboard and minimum stock material, as shown in the video. Add another 10 mm to this to allow for a space called safe travel. Safe travel is where the machine lifts above your stock material and can move from one spot to the next if it needs to, without hitting your project. Most DIY CNC owners won't go above 12 mm diameter tools at approx 100 mm in length. If you research your tooling, you need to know the CEL of your tool. CEL stands for cutting edge length. This is the part that sticks out of your collet. More on collets and parts later. So, let's say your CEL is 50 mm long. So you need to add a mark that is 60 mm above the last mark. Why 60? This is because you need a safety pass for your travel, or as said before, safe travel. You should now have successfully completed two things in one, without even realizing it. Working out your working or cutting depths, and how high you need to make your X-axis components. More on X-axis later. So, the next part gets a little confusing. You need to work out the spindle you plan to use. Why do we jump over here, you ask? The reason for this is you need to be able to work out the rest of the height of your Y-axis plates. I have searched for a few spindle options, but generally a 3 kW spindle will suffice to successfully cut wood and aluminium. So, let's use the following parts for a guide. 3 kW water-cooled spindle. Physical dimensions, 100 mm diameter and a 220 mm length, weighing 10 kilos. So this spindle is 220 mm long. To get the next measurement, you need to take the overall spindle length and add your tool stick out. Remember the part that is CEL? So, for calculation reasons, let's use the above CEL, which is 50 mm. Adding 220 to 50, you get 270 mm. Now you need to work out what 1/3 of this length is, which gives you 90 mm. Okay, so now take the 270, add the 90, it gives you a total of 360 mm. But we're not going to use this exact measurement. We're going to actually find a usable ball screw length for you to use, as these only come in specific lengths. The reason you work out your spindle height is so you don't go and buy linear motion gear that is too long or too short. Longer motion gear can enhance twist and other factors which will ruin your work. In your case, you'll need a length of 400 mm for our calculations. This is the closest to your Z-axis calculation. So now take this 400 mm and add that to your rectangle height. So now you have 32, 100, 10 and 400, which gives you a total of 542. Add a further 50mm to this for securing reasons, brackets or welds. Now you have a total height of 592. This is your overall height of your Y-axis gantry plate. You may be asking, you said we would use RHS tubing for the build. Where are the calculations for this stuff? But just working out your base measurements, you will have incidentally included these already. In this image, I show you where the 65mm RHS tubing goes. But if you choose to use ball screws for your linear motion on your Y-axis, you will install your ball screw mounting brackets in the middle section where I've got the middle part of the RHS tubing. So we have our height. What about the width? So let's start from the left of your rectangle and work to the right. Your first mark will be 50mm. Your next mark will be the width of your RHS tube, which is 30mm. Okay, your next mark from that is 30mm. Okay, this 30mm is for your linear rail assembly. Okay, once the block and linear rail are mated together, they'll actually have about a clearance of 30mm or just more than that. Now comes your choice of linear motion components. When you choose your gear, you have to ensure you match your gear as close as possible. If you can't get something that matches the other, then you may have to compensate with a spacer material to elevate your components. Here I have listed a few suggestions: rack and pinion, linear rails, fully supported round rails, ball screws. In this case, I'll use linear rails and rack and pinion. Industrial machines will use these as they are most reliable. So let's use HGH20CA linear rails with mod 1.5 helical rack and pinion. The linear rails and guide blocks add up to about 30mm combined. We're using the linear rail dimensions from the above link because the rack and pinion are only 15mm wide. You will have to create a spacer to mount these on. Add a mark after your previous mark of 30mm. The next component is your Z-axis to Y-axis mounting plate. This plate will be your choice of material, but in this case we'll use 6mm aluminium. Add 6mm to the last mark. Next on your list is your linear motion gear for your Z-axis. This is the part that lets you move your Z-axis up and down. You're asking, didn't we just cover that? Answer, no. Those were for your Y-axis to move left and right. Anyhow, this is where we have to find our ball screw for our Z-axis. Why the ball screw? Once again, is the item with the greatest height, so we'll use this one. The end supports for these are approx 42mm in height. The other crucial item to obtain in a ball screw setup is the nut housing. So, when you go to buy a ball screw, make sure you obtain a full complete set of end supports, ball screw nuts and nut housing. They will be matched to ensure correct fitting. Avoid buying separate parts as this can lead to wrong choices. So, moving on, add a mark of 42mm to your last mark. Your next part is going to be your spindle mounting plate. This once again will be 6mm aluminium at another mark of 6mm. Your final part, yes, you're looking at your last part, and this is the spindle clamp. You're most likely asking, what about my spindle? But the clamp is the item you're needing to worry about here, as it holds the spindle. Okay, so this spindle clamp bracket has a depth of 95mm from front to back, as shown in the picture. Add 95mm to your drawing, and then finally another 50mm to match the first measurement we used. So let's add them up. 50, 30, 36, 42, 6, 95, 50. Might sound like next week's lot of numbers, but I'm not sure. These total up to 309mm. Yeah, you have your base Y-axis plate size, which is 532 by 309. Now this measurement is not final. You may need to tweak it a little as you do your final drawings, but this plate size will determine all other plates and hole locations. Let's get to setting up your plate design. This will be built inside the boundary of your rectangle. So, given that, this will be the end of this video for today. I hope you've enjoyed this video. If you have, please like, subscribe, share, turn on notifications so that you'll be made aware of the future episodes and what we'll be moving on to. In the next episode, we will move on to your X-axis and your Z-axis assemblies so that you can see how they'll all work together. Okay, if you have any questions, leave a comment down below and we'll see what we can do for you. Thanks for watching. Bye.